Okay, and I think it's time to begin. So today is our last session this year, and our last speaker is Vladimir Rubtsov. You see the title. He will tell us about some preliminary approach to the theory of homotopy structures for the PDEs. And Volodya, please begin. You're welcome.
Okay. First of all, thank you very much for this invitation, and I beg your pardon for possible small and maybe medium problems during my talk. It is the first attempt. I did it, like people say, on my knee because of different obstacles, family reasons, and so on. So I will try to argue that there are something interesting to apply higher structures in concrete computations related to the geometry of partial differential equations. In fact, I'm not completely original, and it's a shame that when we finished the paper, which we wrote together with my colleagues from Santiago, Enrique Reyes, and Clermont-Ferrand, Jean-Pierre Magnot, just when we finished our small paper, it's a shame that we didn't read the very close person work, and I found a talk of Luca Vitaliano where he used very similar idea to apply higher structures to associative higher structures to study geometry of differential equations. The only reason which I think that our paper should be published, and it was published, was because we computed few trivial examples, and Luca didn't. He just proved main theorem, and this theorem, of course, important, but we also gave some examples and computations. So I will also I will describe his results, and I also used with great pleasure some pictures which illustrate some notions from very nice paper of Bruno Valette, Algebra plus Homotopy equal to Operate. Just the archive version which I was used to take pictures. So I understand that maybe my aim just to tell people in this seminar more about algebraic structures and constructions and less about things that they know better than me, geometry of partial differential equations. So I will be pedagogical in the first part of my talk and non-pedagogical just in the second part of my talk. So I will remind what is the main objects of algebraic structures which I want to use here. So the main object is differential graded algebra over some field. Just let's suppose that in my talk mainly it will be real or complex numbers, and it means that this vector space graded by some graded component decomposition. Each component has elements of their own degree, And also, I suppose that this object admits associative operation, which I denote by wedge. So, because it is a kind of superstructure, and multiplication of objects from degree k and degree L gives you objects of degree k plus L. And also, we supply our space with super differential with nilpotency d square equal to 0. And these two operations, they are super in sense that if we have commutation in the product, then the usual rule of signs apply. So A wedge B equal -1 to K times L, B wedge A. And also super Leibniz rule, it means that we have the derivation of wedge product, and when we go from elements of degree k wedge any element, then we have sign minus k in front of the second summand. So it is a standard, what people call Kashul sign rules. Then the operations between such two objects also need to be reminded. So if we have two differential graded algebras, then the homomorphism F is a linear over our scalars map, such that elements of degree k transformed by F into elements of degree k. And also this map preserves wedge operation. So F of multiplication A times B, it's multiplication F of A times FB. And also this operation commutes with differential in both algebras. dBF equal F dA. Commutes without any sign here. Then we can, of course, because of nilpotency of our D, we can define what people usually call homology group H2K, and this is a standard definition. I will not comment this. And if we have this homomorphism F defined as above, then this homomorphism induced homomorphism of algebras in such a way that if we have a class of A, then F star induced map gives you class of FA. We will say that our differential graded algebra is connected if, first of all, zero cohomology isomorphic to the basic K, and if additionally we have triviality of the first cohomology, then we say that our algebra is simply connected. Also, the standard notion of augmentation takes place if we have a surjective map epsilon from A to K, considering like two differential graded algebra morphism, and we suppose that all elements of K have degree 0, and the differential is trivial, then we say that our differential graded algebra augmented. The main example, you know better probably than me. Also, it is so-called differential graded algebra or related to smooth exterior forms on a smooth manifold X. And the corresponding differential is a usual de Rham differential. This example of differential graded algebra is example of simply connected. And of course, the algebra, if our variety X simply connected, then our algebra also simply connected in the above sense. Now, a very important notion of minimality for differential graded algebra. Here, I suppose that our field is real numbers. We will say that differential graded algebra M with differential D sub M is minimal if zero degree component isomorphic to R, and differential is trivial on this 0 degree component. And then the positively graded part, M2 plus, is freely generated by some homogeneous elements x sub 1 xn, such that this part is an exterior algebra of freely generated by these elements x1, x2. And there is finitely many generators of each degree k for each k. If index I less or equal to j, then the degree of the corresponding elements less or equal to degree the other elements j. And also we say that differential d is reducible. It means that if we have element of degree x from the generators x sub I degree k, then the dx belongs to the algebra generated by x1 xi minus 1 elements. We will also say that our minimal DGA is simply connected if the first degree part equal to 0. And in this case, generators xi have degree bigger or equal to 2. And the reducibility means that differential of D plus, it is a subalgebra in the product of M plus wedge M plus. This minimality gives us possibility to define what people call minimal model for differential graded algebra. We say that algebra M dm is minimal model for our differential graded algebra A if the algebra is minimal in the above sense, and also if we have a homomorphism from one algebra to another, which induced isomorphism of homology rings. In this case, this induced homomorphism H star, usually people called quasi-isomorphism. Why all this algebraic formalism and algebraic nonsense, like Lenk called homological constructions, interesting, and from where it came. This notion goes back to American mathematician Dennis Sullivan, who studied in early 70s so-called rational homotopy types. And he proved the following important theorem. If we have a simply connected differential graded algebra A with differential dA, such that all homology groups are finite dimensional, then there exists up to isomorphism unique minimal model for this algebra. What for such theorem serves? Sullivan was interested in the question if the rational when the rational homotopy type completely defined by cohomology algebra. For example, the typical example, very well known is the following. Let's consider a smooth manifold simply connected with P1 equal to 0. And as algebra A, we consider well-known exterior algebra with the differential of DRAM. And then minimal model for this algebra. Also, this model is called real minimal model for manifold X. It is just a cohomology algebra HXR. And it is because this algebra not quasi-isomorphic, but it is just explicitly isomorphic to cohomology of our exterior algebra. So we have this quasi-isomorphism H, which induced this isomorphism of algebras. Another example, less evident, and you will see that it is very important in Sullivan's context, is the Heisenberg group, which represented by 3 times 3 real upper triangular matrices. Let's consider this group of these matrices, and the corresponding manifold X, it's so-called nil manifold, or Heisenberg nil manifold. It's a homogeneous space of this group over lattice gamma, and this gamma is the same matrices but with integer coefficients xyz. Then we can consider differential forms which we denote by omega 1, omega 2, omega 3. Omega 1, it's dx, omega 2, it's dy, and omega 3, it's x dy minus dz. Then these three differential forms, they promise you to define minimal model for this manifold. And this minimal model generated by 3 elements x1, x2, x3, all of degree 1, such that x1 and x2 are closed, and dx3 is a wedge product x1 on x2. The fact that dx3 is non-zero, it will be very important in future. In fact, it means that this manifold has different formality property, and then I want to explain what does it mean. The notion of formality is the following. If we have a minimal algebra M and its cohomology H of M, considering as a trivial differential graded algebra with zero differential, then we say that this minimal algebra is formal if there is a map from this algebra to this cohomology algebra with trivial differential, which induced isomorphism of cohomology. This means that we have minimal model MD for its own cohomology ring. Then we say that this minimal algebra is formal. If we have a formal differential algebra, then of course it is guaranteed that, if its minimal model is formal, then it's guaranteed formality of DJ algebra, and it means that we have isomorphism on the level of cohomology. For example, we will see similar things for the RAM case. If our algebra, exterior algebra for smooth formal, then we say that the very manifold is also formal. So its terminology will transfer to the manifold. So examples of formality, it's very, very rich. For example, all Kähler manifolds. Let's suppose that we have Kähler manifolds X, compact and simply connected manifold. Then we have this formality from which follows from so-called GDEq lemma. The operator DC, it's so we know that on Kähler manifolds we have a complex structure operator I, and so if we have operator DC, which is a composition I2 minus 1 DI, which acts also on differential forms, and then we suppose that it is easy to check that if we take DC differential, which acting on the closed forms, it gives you a subcomplex in de Rham complex with differential D. And then we can take quotient, and DDC lemma implies that there are two quasi-isomorphisms. This subcomplex with DC quasi-isomorphic to the Rham complex and to this quotient. And so it means that we consider this quotient with trivial vanishing differential. So all these two quasi-isomorphisms say that this Kähler simply connected compact manifold is formal. And non-formality, it is our example of nil manifold of Geisenberg. Because let's suppose that we have a homomorphism between minimal model X with differential D and homology with trivial differential, which induced isomorphism on the level of homology. Then we have that element X1 F transforms in non-zero element, element X3, it transforms in zero. It is just easy computation that F of wedge transform to zero. But for this nil manifold, easy to check that wedge product realize non-trivial homology class. So we have contradiction, and our quasi-isomorphism doesn't exist. So it's example of non-formal variety. It was I will say that this non-formality implies many interesting things because, for example, it means that there exist first symplectic but non-Kähler manifolds. It was so-called Iwasawa-Kodaira surfaces. It was discovered by Thurston in mid-70s. And also it is later Duze Magdaf, it seems Duze Magdaf, she proved that there exist also complex symplectic but non-Kähler Kodaira surfaces also in dimension 4. So in dimension 4, this example with Heisenberg-Nil manifold, it is a building blocks to prove highly non-trivial discovery in symplectic topology. Then it was a long story of relation between formality and the existence simply connected non-formal manifolds. And as far as I know, even now, this problem completely doesn't solve. Because, first of all, there was a conjecture that if you have simply connected manifolds, that they are always formal. But then many people, and in particular in Moscow, Babenko and Taimanov, proved that it is not true if the dimension is bigger than 8. Then briefly, it means that at the moment it is not checked only for n equal to 8. In dimension 8, there is still hope that all simply connected 8-dimensional symplectic manifolds are Kähler, but it is not. For other dimensions, this conjecture is wrong. Now, I remind the main hero of this talk, so-called homotopy algebras, associative algebras, or A-infinity algebras. I start with formal definition, and then I will try to explain informally what does it mean. Let's suppose that we have a z-graded vector space over field K, and then a infinity algebra structure on this z-graded vector space is given by a family of graded linear maps, which usually people denote M sub n from tensor degree n of A to A, such that degree of this map is 2 minus n. I just want to remind that it is z-graded, not only positive. If you have only positive, then you should reverse this condition. And also, you have the so-called Stashev identity, Si, of degree n. And this Stashev identity is that the alternating sum of compositions of this linear map, tensor product with identity tensor degrees R and tensor degree P, with this choice of indices equal to 0. And it is Stashev identity hold for all n bigger or equal to 1. Stashev discovered this construction when he studied so-called H space. So he studied topology of loop space of topological space X, and then in homology of loops he discovered such interesting operation. So if we have this A infinity algebra with M sub n, we remind that we use here this standard, as I told, Koszul or Koszul rule of signs. If we evaluate elements F tensor G on elements X tensor Y, then changing of F, X, G, Y application gives a change of sign which depends on degree G and degree F. So if we have homogeneous F and J, of course. What we have as a consequence of this definition? Let's consider small dimension, small degrees, I'm sorry. If we take n equal to 1, R and P equal to 0, and S equal to 1, then we have operation M1. This operation is M1 is from A to A. And this linear map has degree 1. And the condition S, Stashev condition of degree 1, it is just simply condition that M1 is nilpotent. It means that M1 times M1 equal to 0. So it means that M1 gives a d square equal to 0, and in some sense you should suppose that it might be some differential. And this A with M1, it is just a differential complex, cochain differential complex. If we take n equal to 2, then Stashev identity of degree 2 gives you operation from A tensor A to A, and this map is a bilinear map, which you can interpret like a kind of multiplication, and also there is a compatibility with this differential M1, and this compatibility means that we have a graded Leibniz rule with respect to this operation of multiplication. But roughly speaking, we have a not necessarily associative operation. It is multiplication, but not necessarily associative. And if we inspect carefully Stashev identity of degree 3, then we have first equation. It's a composition of M2 times M2 tensor identity minus M2 times identity tensor M2 equal to this expression if we interpret this for n equal to 3. And we can immediately discover that if we suppose M3 equal to 0, then this condition gives compatibility M1 and M2 in above sense. It means that you have a differential graded algebra structure with operation M2 like multiplication and operation M1 like differential of degree 1. So if we have arbitrary differential graded algebra, then of course we can say, oh, it is our fellow A infinity algebra, but all operations in Stashev identity starting with n equal to 3, they are trivial, equal to 0. So it is trivial A infinity algebras. If now we have M1 equal to 0 on the first stage, then algebra A infinity is minimal. And also we can define what is a morphism of two A infinity algebras. If we have A and B, two A infinity algebras, then the morphism, it's a family of maps from A tensor degree n to B, and each map f sub n has degree 1 minus n, such that this condition satisfied for this relation of indices. It's very formal definition. And we say that our map f sub 1 from A with differential m1 of A to B with differential m1 of B. You remember that m1, it's always nilpotent operator. So we have a quasi-isomorphism of A infinity algebras. If we have a quasi-isomorphism of these complexes with differential m1 and mb. So this is a notion transforms to A infinity algebra. Now, let's try to understand informally this formal definition. For this, let's consider the following so-called homotopy data of chain complexes. Let's suppose that we have a chain complex A with differential dA and H with differential dH. And we have a projection P map H of the first complex endomorphism of the first complex H and homotopy condition. So we have two operation from A to H and from H to A, P and I. And homotopy condition is that if we have composition of IP identity minus this composition equal to DAH plus HDA, so this is a connecting homotopy in this complex. So we have the following observation. Of course, if we have a morphisms between these operations, these maps P and I, if they are degree, they are morphisms of chain complex with the homotopy map H degree 1, then we say that if I gives quasi-isomorphism of this complex, then this diagram gives you homotopy retraction. And when the map I is quasi-isomorphism, it means that we have isomorphisms of this complex in cohomologies. Moreover, if we have triviality of this, then we have anti-commutation relations between homotopy and differential in this endomorphism. And then this diagram gives you so-called deformation retract. And then we have the natural question. If we have an associative structure in one complex, when we can transfer this associative structure to another complex, if we have this homotopy data. So can we transfer associative structure from A to H through this homotopy data? Well, let's informally think about it. What our multiplication M from A2 to A associative multiplication means? It means that we have the following relation. So it is associativity condition. Now we want to define on H similar binary operation mu using this some map I, some map P, and our multiplication on A. I and P, they are maps from this homotopy data. So P from A to H and I from H to I to A. We want mu mimic associativity condition, associativity multiplication condition. So first, it should be like a multiplication. So we have this diagrammatically, we have two enters and one exit. And then this operation means that we have I, this tensor square, then we have multiplication M, and then we have projection P back. Let's suppose that I, it's isomorphism from H to A, and I minus 1 equal to P. So it means that we have this condition of deformational retract. Then the answer, of course, yes, this associativity condition on M guarantee associativity condition for mu. But in general, if IP equal to 1 only mod H homotopy, it means that we have some obstruction. This obstruction is called associator. So if you have this condition diagrammatically, then this condition in terms of homotopy data I and P can be interpreted like element in home H tensor degree 3 to H. So this we want to define this like a kind of also a chain complex. For this chain complex on the level of H, we define differential D partial, and if we have element F from this home, then partial D of F we define like our differential DH initial of F minus DH F, but DH now in third tensor degree. So we have a chain complex with this correction of degree F sign. And using this, we have this element which we denote by mu3 with 3 enters. And this element mu3, this our associator. And we suppose that this our associator has degree 1. Since our maps I, P, and M, they have degree 0, and homotopy has degree 1. So proposition is the following. Our product mu2 is associative up to homotopy if mu3 in this complex home H3 to H with differential D partial satisfy this condition. So this associator trivial modulo D of this. So the next step was important, though it was done long time ago. Georgian mathematician Kadeishvili proved so-called Kadeishvili transfer theorem. So what he did? He said, okay, now we have this mu2, mu3, we have this condition, homotopy, up to homotopy associativity, but also we, from this stash of identity, we need some relation between mu2 and mu3. So a part of this condition, homotopy up to homotopy on the level of degree 3, we also should have compatibility between mu2 and mu3. And this compatibility says that it is possible only if there is additional relation. But this additional relation is again not exact, but up to homotopy. And it means that we introduce another linear map, mu4, in Stashev definition, degree plus 2. And now it is element in home H tensor 4H, and so on. So each time we will have satisfaction only up to homotopy with new and new linear map mu sub n. And the short resume that we have associative algebra A infinity only up to homotopy, and we will call it homotopy associative algebra. So formally it is a chain complex which endowed with a family of such operations, mu, m, or mu. In the level of A, it is m. I'm sorry.
It's clear.
Yeah, so degree n minus 2, and they satisfy this Stashev relation. Kdashvili proved that all new operations mu sub n for n bigger or equal to 2, which defined on this chain complex H from given associative product on A by the above formulas really gives the structure which satisfy Stashev relation. So each time when you go from associativity up to homotopy, you obtain this new and new Stashev relation. The next breakthrough was in 98. In 98, Merkulov proposed another transfer theorem. His aim was, I will explain his aim a little bit later. Formally speaking, Merkulov transfer theorem is the following. Let's suppose that we have differential graded algebra with differential D and super commutator with the standard sign rule. And then Merkulov supposed that considering this chain complex, we suppose that there is a subcomplex W and the space, vector space homomorphism Q of degree -1, such that the image of this map identity minus commutator dq always lies in W. Then suppose that we have maps lambda sub n from tensor degree n to A of degree 2 minus n as follows. So lambda 1 is determined only by the condition that composition q lambda 1 equal to minus identity. Lambda 2 just is a product. Lambda 2 of V tensor W equal to V dot W. And lambda n for, sorry, it's a sub here. So it's my fault, I'm sorry. And this is a condition that lambda n equal to lambda 2 applying to q of lambda s and lambda p, q of lambda s and q lambda p, for n bigger or equal to 2. So it is sum over all indices like this. So this condition is also in the assumption of Merkulov. And then he proved the following theorem. We have differential graded algebra with this assumption. And then we can define on this subcomplex linear maps mu sub n, like usual. The first mu1, it is differential, which came from our initial differential of differential graded algebra. And mu mn, it is just a composition of lambda n, which exists by assumption, and this identity minus dq. So it's a kind of homotopy data. It looks like a part of homotopy data. So lambda, it's our previously constructed element, and then Merkulov proved that if we have such definition, then the family of maps M sub n satisfies Stashev n identity, and that's they determine A infinity structure on a subcomplex in A on this W. It is interesting to consider the details because they are useful to in computations. Let's consider the differential graded algebra with differential D and the graded data of degree P, which split it in the following way. Each degree P component, it is a direct sum of ZP and LP, where ZP it's BP and HP, where BP it's just coboundary and cocycles, Z it's cocycles, B it's coboundaries, HP of course it's cohomologies, and then each component can be represented like a direct sum of BP plus HP plus LP. So let's consider as a complex W a direct sum of cohomologies HP, and define a map Q from AP to AP minus 1. I remind you that Q has degree minus 1 in such a way that being restricted to L and H, it is 0. And on coboundaries, this Q is inversion of our differential P minus 1 restricted to L, LP. Okay. So it's easy to check that this restriction on LP minus 1, it is really one-to-one. And then it is because we have a cocycle, but intersection ZP minus 1 and LP minus 1, it's always empty. So it's really a one-to-one map. So we have inversion. Diagrammatically, we have part of our chain complex A, dn minus 1 dn, and then we see how this d acts. On the level of B and H, it goes to 0 in n minus 1. On the level of L, it goes to Bn. And then dn, again, on the level of B and H, it goes to 0. And on the level of n, it goes to Bn plus 1 here. And in its turn, degree minus 1 operator Q, which goes into this homotopy data, of course, it goes from n plus 1 to n, and from n to n minus 1. And on the level of L and H, it goes to 0. And from on the level of B, it goes to n minus 1. It's inversion. So it's very easy and nice, diagrammatically clear. Now, a few comments about this. So this map Q defines homotopy between identity and composition and this projection from A to A. And it is projection from A onto this subcomplex W. So we have ID minus projection, anti-commutator dq plus qd. And then Merkulov assumption takes place with W and Q as we constructed. And because D restricted on HP equal to 0, our operation M1 from Merkulov theorem, it gives you real differential, just zero differential. And mu M2 gives you associative multiplication on W. So because you remember that if the first M1 equal to 0, then the second, it gives you associative multiplication. That's, we can always identify the subcomplex in Merkulov assumption W with cohomology. And so we can, instead of W, we can write cohomology of A, which consequence of all this? Consequence is the following Merkulov theorem, that if we have this function lambda sub n defined in definition of assumption, then the composition mn projection and lambda on the level of this homology algebra gives you a infinity algebra structure on cohomologies with zero first operation m1 and m2 m3 defined by this composition, and family f of compositions of q and lambda n gives you quasi isomorphisms of infinity algebras between A and its own cohomology. So this A infinity algebra, as above, people call Merkulov model or minimal model of DGA by analogy with Sullivan minimal model for DGA, which we considered in the context of rational homotopy theory. And of course, it is the question of what application of all this and why it is interesting such assumption and such construction, special transfer of Merkulov. The question was the following. It is quite nice. Let's go it back to again to a Kähler compact manifold. If we consider two forms, alpha, beta, which are delta closed, I remember that on Kähler manifolds you have operator delta, which is a codifferential with respect to Hodge star. So you have de Rham D, and you have this star delta, delta equal to star D star, maybe up to minus. And it is easy to check that if you have delta closed alpha and beta, the delta of wedge product alpha and beta non-zero. Of course, the first idea how to save the situation, you shall just define new multiplication on the level of these delta closed forms, namely take wedge alpha beta and restrict it on the kernel of delta. So new multiplication given by this circ, it is a restriction of wedge on the kernel of delta. But the problem that this new operation is no more associative. It is, of course, binary operation, but non-associative. What Merkulov checked, he proved that this new operation associative up to homotopy. So it's his construction was used to prove homotopy associativity of this operation. And of course, the same is true for harmonic forms, just for forms which in Hodge theory belong to both kernels. And it is important that what Merkulov discovered, that there are various A infinity structures on compact Kähler complex manifold. Namely, if you have real Hodge de Rham, then you can take as a assumption data as a subspace W, the subspace given by the kernel of DC operator. You remember DC operator, DC, which is E minus 1 D E. And this second part of this data is a Q operator. And this Q operator is a composition of big lambda, green operator for D, and DC. Big lambda, it is a in this Hodge theory, it is a dual operation to multiplication with symplectic structure. You remember that we have this multiplication by canonical to form, and we have a dual operator minus 2, it's given by lambda. If we have instead of DRAM Hodge a complex version of Dolbeau Hodge with double grading, then instead of DC star, we should take star, of course, with respect to the metric. And W space gives you by kernel of D star partial. And Q minus 1 degree operator, it's I times D partial, green operator, which correspond to D partial, and again, this big lambda, which is dual to multiplication by canonical. Moreover, Merkulov discovered that if your Hodge manifold, it is also a Calabi-Yau variety, which means that you have first Chern class equal to 0, or equivalently, there is a everywhere non-trivial section of line canonical bundle, which gives you holomorphic n form, n0 form on this M. Then we have the third A infinity structure, and I will not go into details, but this third A infinity structure relate to so-called Barannikov-Kontsevich DGA, which is defined on, for those who like this Kontsevich formality, it's on the product of exterior TM tensor exterior of exterior algebra of omega 1 of M. So it's forms, and here tensor, and in this complex you have all necessary structures which comes from this Calabi-Yau, and on this complex we have a infinity algebra structure as well on this DG. Okay, now.
Volodya, just a moment. Are you sure that you will be able to finish the talk today? Because,
I don't
well,
know. It depends how much time I have.
yeah, well,
Probably I will stop in couple of minutes, and then
well,
we will decide what to do.
that's what I mean. Maybe we shall make a natural stop somewhere and proceed. We shall discuss when.
So let's discuss. Now I can. What my plan is the following. The next idea was to explain how this Merkulov transform theorem, Luca very straightforwardly used to define A infinity structures in horizontal complex of d phi t. And this is probably for you will be
Yes, but maybe it is reasonable to stop here and begin with the Lucas constructions next time, not to be in a hurry. And
okay. I then
now let us discuss when it is reasonable to proceed, because next Wednesday is Christmas.
next Wednesday it's Christmas. I'm busy.
Yes, then the Wednesday after the next is the New Year. So let me have a look at the calendar. Uh, so then the next Wednesday is Orthodox Christmas. I don't know whether it matters or not. For me, it's no. It's the day after. So maybe we meet on 8th of January. Is it
It,
okay?
for me, it's okay.
Or me too. Alec, what do you think?
Yes, it's okay.
It's okay.
Yes.
So today we stop here, and on 8th of January, Volodya proceeds with Lucas construction. Yes, agreed.
Okay, then
Okay.
thank
Yes,
you for
we
your.
see. Thank you. It was interesting, but it was only the beginning. I also wish everyone a happy New Year, Merry Christmas, so on and so forth. And we, as we agreed, we meet in it seems in 3 weeks. Yes.
Yes, I see that my talk is a good illustration of this joke.
Okay. Okay.
Okay.
Yes, that's right. And your talk is another proof of this.
Yes, yes, of course.
Yeah. Okay. Thank you.
Why?
Have a nice holidays, and we meet in 21 day. Goodbye.
I will start with short reminder, of course.
Okay. Okay. So thank you for being with us, and see you in the next year,
Okay.
hopefully.
Bye.
Goodbye.